Thank you, everyone. Am I audible? Okay, great. Hi, I'm Vaishnavi Nandakumar, and I'm a software engineer at Visa. I love everything related to books, blogs, and open source. I've been contributing to AsyncAPI for the last couple of months as a part of the 2023 mentorship program under the documentation cohort led by Alejandra Quetzali, and it's been an amazing experience so far. It's really nice to see so many familiar faces, people in the audience today as well. So in case the huge title hasn't made it clear already, today I will be talking about request-reply messaging patterns, and more importantly, the real-world use cases we can do so with it in AsyncAPI version 3. But before we get started, I'd like to take some time to explain what messaging patterns are. So given a distributed system, a messaging pattern is basically just a foundational framework you can use for different components to communicate with each other. So given a set of rules and guidelines, we can ensure efficient communication between different entities. So if you can see here, we have a couple of names thrown out: publish, subscribe, message queues, point to point, and yes, at first, it might seem a bit too technical. But at its core, it's a relatively simple concept. In fact, we run into many different implementations without even knowing what goes behind the scenes. So let's make it slightly more fun. I think it's safe to assume that most of us here use social media. Well, the next time you get a notification from the last person you just talked saying that they posted a new photo or started a new live stream, well, you just discovered how publish subscribe works, where you as a user, by following, you're just subscribing to their content. And the next time they post something, you get access to it. Similarly, we have also run into situations, or at least I have, where an OTP on any portal takes at least 20 seconds to come. And boom, you just have 5 seconds to enter it in before you repeat the whole process again. Message expiration queue pattern. It's really as simple as that. And that brings me to the star pattern of today's conversation, the request reply pattern. And this is just a simple example for any e-commerce store. The next time you get something saying, congratulations, your order has been placed. Essentially, it's just a reply to a request that you placed. But we'll be getting more into this topic later on. So over the next couple of slides, I'll mainly be describing what request reply is, how it can be used in an asynchronous system, the difference between the implementation in version 2 versus version 3, and finally, we'll get into some interesting use cases for today. So when you think about it, request reply is just a two-way communication. You have one component called the requester, another one called the replier, and it sends a reply, mimicking a very traditional conversation. Now over here, as you can see, I have implemented a very, very basic diagram. It could basically be a synchronous system. Requester sends a message, waits for a reply, and then it receives a reply back. The keyword here being wait. But what if one component crashes? Or worse, what if you want to scale up? The whole operation comes to a stop. And that is where we have request reply in an asynchronous system. So in an asynchronous system, request reply is generally implemented by making use of different channels. So as you can see in the diagram over here, you have one called a request channel and another one called a response channel. And Mr. Harikrishnan's PowerPoint also had a wonderful use case of that, if you must have noticed. So this channel can be anything from a queue that you've implemented to a Kafka topic. That's completely up to you as a user or a developer to decide. But the main point being, over here the requester sends its messages and doesn't have to wait for an immediate response. The reply takes it in from the request channel, processes it in its own time, and pushes the response back into the response channel. This enables parallel processing, fault tolerance, and scalability, but most importantly, it is a decoupled system. So if one component crashes and burns, the entire operation doesn't come to a halt. So with that, I hope you got a good understanding of how it can be implemented in different systems. And that brings me to the changes in implementation in AsyncAPI from version 2 to version 3. So up until version 2, we used a publish subscribe operation object. which made it very difficult to directly implement this messaging pattern. So if you can see over here in the highlighted code, we use specification extensions to directly imply the sort of response that you're supposed to receive. However, with version 3, we've completely removed the publish-subscriber confusion by instead replacing it with the send-receive operation object keywords instead. This offered a much more straightforward implementation of the request-reply messaging pattern with the help of the reply keyword. And over here, as you can see, it's very direct, and I'll be getting more into this later on. But it also allows you to accommodate several sub-patterns, each of which I'll be explaining as well. And that brings me to my first use case of the day, a simple static order service. So by now, you must have gotten used to this diagram being thrown around in my presentation. But the use case here is very simple. You as a user, you're going into an e-commerce store, you're placing an order. It gets pushed into an order queue, gets processed by the replier, and the order status is pushed back into the status queue. And let's say, as the requester, you can access it with the help of an API endpoint. You can also note that the order schemas we're using are very different. So for the order schema, we have the order ID, category, category code, timestamp. But for the status payload with what the replier is sending back, it's fairly simple. You just have an acknowledgement status and the order ID, that is the identifiable attribute. With this being said, let's move on to the studio. Is this visible? Like, it's readable, right? Or should I zoom in more? Perfect. Okay. So I'm assuming most of you in the audience are familiar with what an AsyncAPI document looks like. But if you are new, the left-hand navigation, as you can see over here, is a fantastic way that provides a very structured and a concise structure of what our document looks like. So just like I've mentioned before, we have an order queue, a status queue. The address is further defined over here, each of which corresponds to a different message, just like the message schema like I'd shown in my PPT. So as you can see, we have several attributes defined in the schemas, and this is just a general outlay of what it would look like. The main thing that we'd be getting into would be under the operation section. So a very important thing to note here is that we are writing an AsyncAPI document to describe the replier. So in this case, we set the action tag to receive. So we are receiving an event payload, processing it, and replying back to the response channel. I hope that flow is clear. So if that is, we can go line by line. For my operation, get order, where I've set the action to receive, I am getting the order from my create order channel, following the message schema like I defined before. And the reply goes back into the set status channel, which is basically the response queue. It is as simple as that. This was a very direct use case with two separate channels, two separate messages corresponding to each. And the entire operation can be defined for our replier over here within what? 10 lines? That's pretty much it. But let's go one step further now. Let's say we want to scale our system up. Let's make it more dynamic. Now in this case, to prevent congestion in one response queue, we've decided that for every request that I get, I want to send my reply back based on the category code of the order received. So let's say I have a fashion item order coming in. I'll let it go into response channel 1. Or electronics, that goes into response channel 2. Now the thing with this use case is, the message schema, the number of channels all stay the same, but the address at which it would be sent is determined at runtime. It's more dynamic in nature. So how can we go ahead and describe that? So let's just add one more component. We'll say that in my request, I will define the reply topic, which it's supposed to go into in the header of the payload. So to represent that in our AsyncAPI document, it's very simple as well. We'll start off with the first step. The set status is the only defining factor here. The one thing that you'd notice is that we'd first set our address to null. It's not static anymore. It'll be changing based on every request that we receive. Rest of it stays the same. Operations, once again, we're writing this for the replier. So our action would be to receive an event. We go further down. We define the channel which we get the request from. But in the reply, you'd notice one change. We've added an address component here too. But more importantly, we've defined the location. And this location here tells you where to look for to get the address of the response channel at runtime. So if you look over here, I've clearly defined when I get an event, I go into the message section in the header, and if I look at the reply topic attribute, I'd get exactly the address that I'm looking for. So I've also, I can expand on the message as well. I've clearly defined my header here, and this is where the location would be pointing at. And that's it. You've implemented a dynamic subpattern use case as well. So up until now, we have had two separate channels, one for request, one for reply. There's been a very clear distinction between both of these. But what if we just had one channel for both? Would that be possible? And that brings me to my third use case. So quick show of hands, how many of you are familiar with WebSockets? Okay, awesome. So over here for my third use case, I have an example for a simple WebSocket chat application. So for those of you who are not familiar with it, a WebSocket is a communication protocol that enables bidirectional data exchange over a single long-lived channel. So if you take a chat application, very, very basic diagram again, by the way. I have a requester user A, my friend is user B, the replier, but I am sending the same message back and forth. There are no separate message formats that I'm expecting over here. So if I'm writing an AsyncAPI document for user A, I am sending a message. So the action tag over here would be to send. I'm sending a schema following this format, user ID, text, timestamp, and I'm expecting to receive the same message back. Now over here, things can get, I think simplified would be the right word. But compared to our previous examples, if you look over here, we just have one single channel, one schema, one message. Everything's much simple. So when you look at the operation, the same thing applies. The only difference being over here, just for a change, I decided to write my AsyncAPI document for user A, the requester. And the only change factor that comes in is that the action over here would be to send. If I'm going through this line by line, I am sending through this send chat channel, which again is WebSocket, with following the message schema. So over here under chats, I've defined all the attributes I've needed as well. And I'm expecting a reply with the same channel. There is no other information that I have to get because it's the exact same thing that I'm expecting to receive back. So there is nothing, no other extra step that you have to mention, and this use case is very straightforward as well. But over here, if we're going one step further, what if I had two different messages expected out of one single channel? And that brings me to my last subpattern of the day. And personally, I thought this was the most interesting one. Just to give you some background context, a couple of weeks ago, I had to create a custom Slack bot. Now, the purpose of my Slack bot was to monitor my Slack workspace channel, and every time a user added an emoji to a message in any channel, the Slack Events API would send me a reaction payload saying that, hey, this is the message to which a user has reacted to with this emoji and so on and so forth. Exactly, as you can see in the reaction added schema. I've represented this in the diagram as well to give you a basic flow. But the thing is, when a user added an emoji and I get this payload, Slack server would keep on sending me the same thing over and over again until I sent an acknowledgement back saying, listen, hey, I've received it, you can stop trying. So that was important. And that acknowledgement schema followed a much simpler message format. The only difference being it needed the same envelope ID like I had referenced in the reaction added schema, and even the payload according to the Slack documentation was just optional in nature. Another important thing that I missed out was that the whole thing was done using Slack socket mode, which employs a WebSocket protocol. So over here we have one single channel, but two very different messages or events expected out of it. So how do we implement this request reply use case to clearly specify which message was expected out of which event? And that is what would bring me to the last document of the day. Everything else stays the same, except for this section first. Let's go with this line by line. So in our previous example, for every single channel, we just had one message. But in this one, as you can see with version 3 as well, we have more of a key value structure where I mentioned the reaction event, which follows this given payload, and the acknowledgement schema, which just has an envelope ID and the payload property. I've mentioned both of these for this one channel. But a more clear distinction comes under the operations section. So I am writing this AsyncAPI document as a part of my Slack application. So I'm set to receive events. So if I'm going with this line by line, for my reaction listener operation, if I'm receiving an event from my root channel, I have to clearly specify which message or which type of event I'm expected to receive. And that would bring me to this attribute, the messages attribute you can see here. This wasn't defined in our previous examples, but since this is a case which just has one channel and multiple messages, it's very important to define this here. And the rest of it goes the same way as well. We have our reply object keyword. And even here, I'd have to mention which message I'm expected to reply with. That is the acknowledge message. Once again, the same channel is being used. And that's pretty much it. So over the course of these 4 documents, you've learned about 4 different sub-patterns. We've had a static example, a dynamic example, a single channel use case, and one which accommodates multiple messages. All of which follows the same format, but the only distinction in being what exactly or what is something extra that you might have to define. And with that, I hope you got a good understanding of what request reply is. It was as simple or as easy as a use case it was supposed to represent. And that brings me to the end of my presentation. So I'm opening the floor to any questions. Okay.
Typically, when you say request reply, there is an associated timeout.
Yes.
So how does it work here?
So we haven't defined timeout as such. Most of it is just going with the request reply headers or the keywords, and it's just representing the channels it would go to. But I would like to get back to you on that. Yeah.
The reason is request reply is more on implementation.
Yes.
Right? When you're making it part of the spec, um, most of the places what they do is they create a temporary channel.
Mm-hmm.
So you send in a request, and then you create a temporary channel and expect a response on that channel.
Okay.
Once the response comes back, that channel will be destroyed.
Okay.
Right? That's how I've seen.
Okay.
But this makes it look like a channel-centric activity. So what it means is now you have the overhead of maintaining this another channel.
Mm-hmm.
And then how are you going to protect from somebody else dropping in messages into that channel?
Okay.
So it opens up more questions. I'm sure they must be answered,
Mm-hmm.
but just got curious.
So when you were talking about temporary channels
Mm-hmm.
and channel-centric, the only difference would be the messages get redirected to that channel, right? And if I want to represent it that way, I just have to change the names in our channel over there.
That's what I'm saying. You
Yeah.
don't need to.
Yeah, okay.
That's a temporary. The whole
Yes.
purpose is temporary. You don't need to create or manage those things. That's one approach I've seen
Okay.
prominently used. I'm just curious if the spec covers that.
Okay, but I'd love to get back to you on this
Sure.
as well.
Thank you.
Just a follow-up on that. So usually in OpenAPI spec, we have something like URI params, where I can have a dynamic value. Just follow up of the temporary queue.
Okay.
I can actually define how the temporary queue will be, the channel will be defined. Is there any scope for that?
Okay, so this could correlate with the dynamic sub-pattern I've described as well. Okay. We use a location tag for my second use case over here. So in this case, what I'm basically saying is that the category code is a dynamic value that would be changed for different events, right? If I'm understanding correctly.
But if a temporary, if I have to create a temporary queue, for example, let's take UUID. I generate a UUID, and that is a channel I want to create, for example, okay? So that is a dynamic value which I don't know before. Here, though it is dynamic, I am defining the channels. There are 3 channels or 4 channels. But there it is unlimited channels.
Okay, same thing. But over here, like, so it's an attribute in the payload, is it? Yeah. So in this example, if you can see, I've mentioned the category code attribute as well. So you can easily reference that.
You can use this pattern for temporary queues.
Yeah, but
Maybe
we
that's
could
how it
have,
works,
I
I
could
think.
share this document to
Yeah.
you as well.
I think without this, right, the correlation becomes a problem.
We can add correlation ID.
Correlation ID is something which is
Great. Any other question?
Depends on the underneath the underlying EDA, how they treat the topic. If it is Kafka, it's a string literal. There is no more room for you to capture the context. But if it's other broker like RabbitMQ or Solace or something, they have this hierarchical notion. So this, whatever the thing that you're referring to as a category code, anything that's part of the payload, you can promote it and make it part of the topic. That will help you with more routing governance.
Do we have any more questions? Thank you so much, Vaishnavi.